It's like I said a couple of minutes ago, it's a two-step process. First of all, you have to figure out the direction of the magnetic moment. And then once you know that, what's the direction of mu cross B? So, well, just to run through the answers quickly, first of all, and then I'll explain them. Part A, the torque vector points in the plus y direction. Part B, it points in the plus x direction. And in part C, there is no torque. The torque is 0. So part A, plus y for the answer. As for the reason why, you've got this circular loop. Now, whether it's a single loop of wire or any kind of a coil, the magnetic moment points along its axis, okay? So the magnetic moment, mu, must be either pointing out of the page toward you or through the page away from you. And the way you choose between those two alternatives is you grab the coil, or in this case it's just a single loop, with your fingers pointing in the direction that the current goes around. Your thumb points in the direction of mu, the magnetic moment vector. So that little dot there, arrow pointing this, or, you know, it's the same thing anytime you run into anything to do with the right-hand rule. Last fall when we were doing torques, same thing. Counterclockwise is positive, clockwise is negative. So if you got a current going around this thing counterclockwise, the magnetic moment vector is going to point in the plus z direction. If it's going around the other way, clockwise, then you'd have a little x there instead of a dot. So that's step 1. And then step 2, if that's the mu vector, and if that's the B vector, maybe I'll do my pencil trick again. You've got an arrow like that, and you've got an arrow like that. So their cross product has to be perpendicular to both of them, which means it's either up the y direction or down in the negative y direction. To choose between them, mu cross B, your fingers go from mu toward B, looks like your thumb points up that way. Or alternatively, you can just sit on your right hand, and well, that won't work if you're right-handed, but you can you know, do the little circle with the I, J, and K going around it, figure out the direction of the cross product that way, and that's a variation on the idea. For the next one, as I said, the answer comes out positive X. So this time, the current, probably should have labeled that I. This time it's going around the loop counter, or this time it's clockwise. Opposite direction for the current means the opposite direction for its magnetic moment. I times A, once again, is what the magnetic moment means if you don't quite remember from the other day. So then you have to do the cross product, where that's mu and B, like it shows in the picture, is pointing up that way. So mu cross B, that would be positive X direction. And then in the last part, the issue is that the magnetic moment points in, let's see, the positive z direction. That's the same as the first one, I guess. Any cross product is the magnitude of the one vector times magnitude of the other vector times the sine of the angle in between. Well, if both vectors point in the z direction, we're talking about the sine of 0 degrees times the other thing, but parallel vectors have a cross product of 0 always. Well, the last thing I put in section 7, we'll get part of section 8 before today is over with, but I threw a page on the end of section 7 with the title, "What is a magnetic field really?" Well, to actually fully explain what a magnetic field is, you have to get into the special theory of relativity. If you take a higher level electromagnetism course, the textbook might very well have 2 chapters on special relativity, because ultimately magnetism is a relativistic effect, which I will try to explain in 5 minutes or less. Yeah, wish me luck with that one. But just kind of skimming a few little points off the surface here without trying to get into it in, well, I spend a week on it in Physics 133, and even that's a fairly superficial treatment of the subject. But it turns out that when things are moving close to the speed of light, this Newtonian mechanics that I spent a whole semester making you try to learn, yeah, when you get really close to the speed of light, it's sort of wrong. Parts of it are anyhow. Still worth learning, because at speeds you encounter every day, you know, really low speeds, like some spacecraft that's been shot toward the moon, or a bullet going 3 times the speed of sound, you know, really low speed things like that. Newtonian mechanics works perfectly for any reasonable level of accuracy you might be worried about. But it turns out to just be a low speed approximation to the principles that apply in the theory of relativity that was developed a little over 100 years ago. It turns out space and time are not absolutes, okay? Newton assumed that space and time were absolute and speed is relative. See, relativity is about different frames of reference. It's about relative motion. If you're sitting on the back of a pickup truck and the truck's going down the road at 30 miles an hour, no, let's make it 20 miles an hour. You've got a friend on the side of the road and you decide to throw a baseball to your friend. You throw the ball at 30 miles an hour. Your friend catches a baseball that's going 50 miles an hour. The ball's speed is 30 miles an hour relative to you, but it's 50 miles an hour relative to your friend on the side of the road, because your frames of reference are moving relative to each other at 20 miles an hour. Well, that's the common sense way that things work at low speeds. Yeah, this can be the problem with common sense. Put a lot more zeros on all the numbers. If you're in some spacecraft going 2 times 10 to the 8th meters per second, and this is just a hypothetical, where this actually comes into play is with elementary particles. It's really easy to get electrons and things going this fast. Spacecraft are so much more massive. any imaginable technology wouldn't get it going this fast. But just as a thought experiment, you're on the spacecraft going 2 times 10 to the 8 meters per second, and you have a laser pointer. And you point it at your friend who's standing there on the Earth, and you measure the speed of the light coming out of that laser pointer, and it's 3 times 10 to the 8 meters per second. Your friend measures the speed of that beam of light as it hits them and gets 3, not 5, 3 times 10 to the 8th meters per second. Speed of light in a vacuum turns out to be a universal constant, just like the gravitation constant and the gas law constant and all of those numbers that describe the basic nuts and bolts of our universe. Speed of light is not relative. It's not different to different observers. And I've already used up the 5 minutes, I think, that I wanted to spend on this whole story, but what I'm leading up to is that if the speed of light is not different to different observers, since speed is distance over time, it must be distance and time that are different to different observers. If there's a spaceship moving away from you at a very high speed, Darth Vader leaving the Death Star, and you're standing there watching him go, okay? And let's say he's got a big clock mounted on top of his ship where you can watch the clock run through a telescope. Darth Vader's ship is going to be shortened along the direction of motion, not to the sides because there is no motion in those 2 dimensions, but along the direction of motion, things near the speed of light get shortened and time runs slower as the second hand on Darth Vader's clock ticks ahead 1 second, maybe depending on how fast he's going, maybe 3 or 5 or 10 seconds goes by on your wristwatch, okay? So with that in mind, let's consider 2 electrically charged particles, like I talked about when I came in here the first day, a couple of pith balls maybe, or a couple of protons, whatever they are. They exert a force on each other. If they're both positive, it would be a repulsive force, like I drew it here. Let's imagine looking at this situation from 2 different frames of reference. This coordinate system, x prime, y prime, and z prime, has its origin at this charge here. So in this coordinate system, those 2 charges are at rest. Seen from this other frame of reference, the charges are both moving toward the right with a speed that I call v. Well, in the primed frame of reference, the charges are at rest and they behave exactly the way I was talking about in section 1. The force would be given by Coulomb's law, and the direction of the force on this charge would be directly away from the other charge. Seen from the other frame of reference, distances along the x-axis get shortened. Distances along the y-axis do not. So you can see that this angle theta would be different. Seen from the unprimed frame of reference, theta would get bigger compared to what it is in the primed frame of reference. And that's by no means the whole story, but let's say it's among the factors that means that the direction of the force is no longer right exactly along the line that connects the 2 charges. It's a little off to the side, like that. So let's take that force and, in a sense, break it into 2 components. Now, normally when you use the word component, you mean with respect to 2 perpendicular directions, like x components and y components. But this time, let's do it this way. Let's have one so-called component be along the line that connects the 2 charges. And I'll call that component the electric force. And the other component would be along the direction perpendicular to the velocity v. And I'm going to call that component magnetic. Okay, so The force that the one charge exerts on the other is just plain F. And I'm saying that F is the vector sum of Fe plus Fm. So, for example, if you have two current carrying wires, as in this afternoon's lab, well, it's actually going to be two bunches of current carrying parallel wires in this afternoon's lab, but the simpler case would be just two wires. Both wires are full of electric charges. There's the electrons, and then there's the surrounding metal ions. And they exert forces on each other. But because there are equal amounts of plus and minus charges in each wire, the electric component is 0. But because the electrons are in motion and the surrounding copper ions are not, well, there's no drift velocity anyhow for the copper ions. That means that the magnetic components do not cancel out. And so this force exists because of the charges being in motion. Now, relativistic effects are normally something you only have to worry about at high speeds. If you're talking about the usual 3 significant figures, that is kind of our standard for homework problems and exams and so on, you're talking about, as a rounded off kind of crude number, somewhere around 10% of the speed of light. If something's going 10% of the speed of light, the third of your 3 significant figures starts to slightly be affected by relativistic effects. The drift velocity, as we saw earlier in the course, the drift velocity of the electrons in these wires is less than a millimeter per second, which is tiny compared to the speed of light. But I said you didn't have to worry about it until around 10% of the speed of light if you're working to 3 significant figures. Now, I've got some rough calculations roughed out on this page here that I'm not going to bother to trouble you with the details with, but if you add up the charge of all the conduction electrons, the free electrons in each of these wires, well, depending on how long the wires are, but if they're like, 50 centimeters or a meter long or something like that, you're talking about a couple hundred coulombs worth of charge. And if the wires are a centimeter apart, which is roughly what you'll have in today's lab, you're talking about something on the order of 10 to the 18th newtons for the electric force between the electrons in this wire and the electrons in that wire, which, like I said a minute ago, is exactly canceled out by the electric forces in the opposite directions between the positive copper ions. The magnetic force, as you'll find when you do the lab, is on the order of a few thousandths of a newton. So 10 to the positive 18 compared to 10 to the negative 3, that's 21 orders of magnitude difference here, okay? So this kind of thing, yeah, you don't have to worry about it until 10% of the speed of light if you're talking about 3 significant figures. But if you're talking about numbers where you're going to like 21 or 22 significant figures, numbers this long, then yeah, relativistic effects start to show up in the last couple of digits for things that are only going a millimeter per second. And so that is what magnetism is, really. It's a distortion of the electric field that you get when the charges are in motion. And in fact, that's, from a theoretical point of view, that's where the theory of relativity came from in the first place, is Einstein was disturbed by the fact that Maxwell's theory of electromagnetism was inconsistent with Newton's theory of mechanics. He was trying to create a mechanics that was consistent with the laws of electromagnetism. So anyhow, that's where magnetism comes from. It's a relativistic effect, a relativistic distortion of an electric field. It's due to the source of the field being in motion. Okay. Section 8. And if I was a good teacher, I would have set this up before class, and I didn't think of it till just now. I've got a little demonstration. I'm just going to pause this. It'll just take me a moment to grab this out of the back. So, as those of you who are watching from home just missed, because I couldn't really think of a good, I've used up all the outlets here on the front desk already, and I couldn't think of a good way to get it on the camera. But sometime when you're in here doing a lab, ask me to show you if you want to see it. But I had a wire pointing vertically, and I had a magnetic compass sitting next to it. And what people could see is that anywhere I put that compass, it pointed in a direction tangent to a circle around that wire, kind of like it shows in the diagram over here, except the thing that I did had a vertical wire and this is a horizontal wire. But, it's the same picture, just turned sideways. The direction that the field lines go around is right-handed. Grab the wire with your thumb pointing along the direction of the current, except remember I'm not supposed to say the direction of the current, but I don't know what else to call it. And so your thumb points in the direction of the current, fingers wrap around it, pointing in the direction of the field lines, which in this example here is up the back and down the front. Okay, so I believe I made a little sketch of some badly drawn right hand next to a current carrying wire on your formula sheet to kind of remind you how that works, but that's how it works. So magnetic fields are found around current carrying wires, which is to say magnetic fields are found around electric charge in motion, kind of like I was saying right at the end of section 7 a few minutes ago. Current is in a wire, charge is moving through the wire. It's just two different ways of saying the same thing. The basic equation of magnetostatics, in other words, unchanging magnetic fields, or I guess you could call it a DC magnetic field. The basic equation that describes that is called Ampere's law. And it goes something like this. Gauss's law, remember, was the basic equation of electrostatics. That involved a surface, okay? You had to pick some closed surface, and the total flux through that surface was proportional to the charge inside of it. Ampere's law uses a path rather than a surface. So you have to pick some closed path, closed meaning that if you follow it for long enough, you end up back where it started. So Ampere's law, pick a closed path. If, just as an example, if you're talking about the field around a straight wire, there's the wire carrying the current I. And a good, well, it could be any, in principle, any path. It could be a square, it could be something shaped like a star. But what's going to make the math the easiest would be a circle. centered on the wire. So just to kind of draw it as if you were looking at it from an angle. Something sort of like that. Before I get too sophisticated with the notation, the basic idea is that strength of the field along that path times the length of the path, which in this case would be the circumference of the circle, is equal to a fundamental constant called the permeability of a vacuum in SI units. Unlike some other fundamental constants that we've encountered, which have to be measured by some sort of experiment, mu naught is defined to equal, if you've got a definition for an arbitrary definition for the Tesla and an arbitrary definition for the ampere and so on, because that's the thing I haven't written down yet, is the current through the path. You can define your other units in such a way that makes mu naught exactly 4 pi times 10 to the negative 7. Its name, once again, is the permeability. Free space just being another way of saying a vacuum. And if you don't happen to remember that, you can look it up in the same place where you look up other fundamental constants like the elementary charge and the Coulomb's law constant. It's all in the same table there. So the length of the path times the strength of the field on it. Maybe it helps you remember it if you notice that it rhymes. I mean, these kinds of things are kind of silly and embarrassing to stand in front of a class to say, but it works, The length times the strength is proportional to how much current passes through that path. And that's the basic idea behind Ampere's law. Now, just like when we were doing Gauss's law problems, sometimes you had to break the surface into different parts and add up, like if you had a box, flux through this side plus the flux through that side and so on. Well, sometimes you might need to do the same thing here. If necessary, break the path into pieces. So to get the total along the entire path, you'd have to add up. It's a dot product. When I said times over here, the strength times the length, times is the dot product of these two vectors. Okay. B would be measured in Teslas. S would be measured in meters. That's like if you imagine moving along this path. This would be the displacement vector. So for anything I'm going to throw at you anyhow, that would be the practical way to look at Ampere's law. But of course, the most general case would be if you've got a field that's varying continuously from one point to another, you wouldn't be able to break the path up into a finite number of pieces, each with a finite length. You'd have to take the limit of infinitely many, infinitely small pieces. And so for the left side of the equal sign here, the most general way of writing Ampere's law would look like that. And just like there was a little circle on the integral sign when I talked about Gauss's law to indicate that you have to integrate all over a closed surface, well, there's a similar meaning here, except it's a one-dimensional integral instead of integrating over a surface. So this time we're talking about over a closed, that you have to integrate around a closed loop. So the little curly Q on the integral sign is just to indicate what you should be picking for your limits of integration. You should be picking limits that cover the entire loop all the way back to some starting point. So that's Ampere's law. Very general principle. And what comes next is how to get what's going on in specific cases from it. Kind of like Gauss's law several weeks ago was a very basic general principle. And how do you figure out what the field of a long straight wire is from that? How do you figure out what the field of a charged sphere is from that? Same sort of thing here. Let's look at a few examples of getting the formula for some special case from this much more general, more or less first principle. So the first, I put down kind of a step-by-step recipe that you can refer to as you're looking at this in your homework. Have a good trip. And the first actual example down there, 8-1, is the straight wire I've been talking about. So I can at least get through that in 15 minutes. So step one. Well, the step one when I was doing problems with electric fields for Gauss's law was before you can do anything else, you have to have some kind of a picture in your head of what the field looks like. And that's the first step here also. So in this case, I've already pretty well covered what the field of a straight wire looks like. I showed it to you experimentally. It's loops around the wire. So the field circles around the wire. I'll just write that down for the sake of completeness, but I've already kind of done that. Step two, Ampere's law refers to a path. So you have to have a path in mind. And as with choosing a Gaussian surface, you want to choose a path. Hopefully there's a path exists where the field keeps a constant strength and also a constant angle. There's that cosine factor that goes with the dot product. You want to keep a constant strength and a constant theta all the way along that path, because that's going to make the math a heck of a lot easier than trying to integrate around some star-shaped path or or some bad choice like that. So here, where the field lines are circles, well, like I already mentioned back over here, a good choice would be a circle centered on the wire. In other words, take advantage of the symmetries in the problem. So for my path, I'm going to use a circle that goes along one of the field lines. And I'll draw a little picture here. This would be an end view, as if the wire was sticking out of the page, current flowing toward you. So we got the current flowing out this way through that wire in the middle there. We are interested in some point. That's the point where I want to know the magnetic field. Find B a distance r from the long straight wire. So there's r. And my point P is a distance r from the center of this long straight wire. That's where I want to know B equals what at that point. Well, if you divide this path into small pieces, such as this one, or it could be somewhere else, like over here. Or even over here. Anywhere along that path, the direction of the field is parallel to that small displacement vector. Direction of B over here, that way. That was the direction that when I did the demonstration, that's the direction the compass would have pointed right there. This is the direction that the compass would have pointed right there. This is the direction that the compass would have pointed right there. So what I'm saying is anywhere on that path, the angle theta between B and ds, because we got a dot product here, B dot ds, anywhere along that path, theta equals 0 degrees. So the cosine factor is always just equal to 1. Furthermore, every point along this path is in exactly the same situation as any other point along the path. I could take this picture, I could rotate it 41 1/3 degrees, and you would never know. It would look exactly the same. So therefore, the strength of the field, B, is the same everywhere along that path. And so we don't need to actually perform any integral. Everything is constant as you go along the path. Well, going with what I have written in the box, it says the summation of B cosine theta times S, the dot product, but you don't need to break it into several pieces. Just for the entire piece, it's B cosine. It's a summation with one term in this case. B is my unknown. The cosine factor is equal to 1. S, remember, stands for the length of the path. This is the strength times the length, and it's a circle. Circumference of a circle is 2 pi r. Step 4. Set it equal to mu naught times I. No, that's not going to take very long. And finally, solve for B. Also not going to take very long. And if you were to refer to your formula sheet, you'll find that that's listed under section 8 as the formula for the magnetic field around a long straight wire. I is the current in the wire, R is the distance from the center of the wire to the point where you're calculating the field. Well, let's see, I guess there's a few more comments to make that'll fit into the 5 minutes I've got here. I don't know as I've got time to get into the next problem, but there's a little stuff to say before I get to problem number 2. So, what if it's not a straight wire? I mean, sometimes you're dealing with straight wires. Today's lab you are. But a lot of times you're dealing with coils, like the one that you guys just couldn't put down the other day. So if you've got a circular loop instead of a straight line, well, let's look at that as far as what the direction of the field would be. If you've got a circular loop, a small part of the circle looks pretty straight. Like, if I magnify the living daylights out of it, you know, continues, I'm not going to bother drawing all of it, but if you consider just a little piece of that loop from about there to there, it looks almost like a straight piece of wire. So if I apply the right-hand rule to that, the way I was saying it before, you've got a wire, and you grab it with your thumb, pointing along the current, and if you do that, your fingers wrap around that wire, pointing in the direction of the field lines, which in this case would be into the page over here. So I'll draw a couple X's. And it would be out of the page over here. So put a couple of dots. And so that's how you could look at the situation in terms of what I've already said earlier. But the way they usually look at it is to say, let's make the picture a little smaller here. Got current flowing around the thing this way. Grab the loop or coil or whatever it is. Grab the coil with your fingers pointing in the direction that the current flows around, which in this case is clockwise. Thumb points in the direction of the field inside of it. Magnetic field lines are always closed loops. They never have a beginning or an end. So all of the field lines that thread through there in the one direction, through the inside of it, they have to come back the other way around the outside of it. But the right-hand rule gives you the field in here, which comes out the same as when you look at it this way. But people usually look at it that way. I would demonstrate with the actual coils we had the other day, but they're put away at the moment. But you grab it, your fingers point in the direction. I think there's a picture of this on the formula sheet too. Fingers point in the the direction of the field is there. So at the very bottom of the page, I've drawn a solenoid, which is a word that basically means long coil. We've got formulas on the formula sheet for two opposite extremes, okay? One is a coil that's very short compared to its diameter, and that's one formula. And the other is for a coil which is very long compared to its diameter. In fact, for the formula to be perfectly true, you'd be talking about an infinitely long coil. And that's a completely different formula. But the long coil is what the word solenoid means. So there's a picture, and there's a little picture of a right hand next to it, and it's what I was just saying. If you grab this with your fingers wrapping around it in the direction that the current flows, it should be up the back of the picture and down the front of the picture. Notice that your thumb points in the direction that the field lines go through the interior. Or another way you hear it phrased sometimes is people say that your thumb points north, because the field of a solenoid is pretty much identical to the field of a permanent bar magnet. And the end where the field lines come out, that's the north end of a magnet. The end where the field lines go in, that's the south end. So either way you want to put it. That's the direction of the field inside. The field outside is much weaker because there's a lot more space for the field lines to spread out. And more on that when we reconvene after the break. First example I'll do will be to get a formula for the field inside a solenoid. But this looks like a good place to leave off for today. The answer sheet for the lab is